Hey Chemistry, Mrs. KJ here to go over 8.06 Transmutation of Elements. Nuclear science realizes the medieval alchemist's dream of changing one element into another. In medieval times, alchemists dreamed of changing elements like lead into gold. Their experiments failed to meet their dreams but wound up laying many foundations for modern chemistry. Radioactive decay of unstable nuclei naturally changes one element into another via transmutation. However, modern technology can also change elements. In this lesson, you will learn about transmutation, both natural and artificial, as well as particle accelerator technology. Transmutation of elements occurs through decay of natural radioactive elements. It also occurs through the collision of atoms at high speeds. Goals for this lesson: identify naturally occurring isotopes of elements that are radioactive, identify isotopes that are formed from nuclear reactions, define transmutation of elements. And you can get the student guide from slide 2. Medieval alchemists worked to turn lead into gold. The predecessors of modern chemistry were the alchemists. In medieval times, they toiled away in their laboratories trying to change common metals such as lead into precious metals such as gold and silver. They believed that an important but mythical tool called a philosopher's stone was essential in the process. While they never succeeded, their investigations led to many chemical discoveries and technologies, such as distillation, metalworking, and refining to produce dyes, paints, extracts, liqueurs, and other products. What alchemists did not realize was that nature was already turning some elements into others through radioactivity, the decay of unstable atomic nucleus, followed by the release of radiation. Radioactively decaying atoms release matter or energy. Upon breaking down, unstable nuclei release energy of 3 major types: the alpha particle, a helium nucleus, 2 protons, 2 neutrons, often released from a large atom; beta particle, a high-speed electron from the nucleus, not from the orbitals; gamma ray, electromagnetic waves. Besides these major types of radiation, some nuclei can emit a positron, a positively charged particle similar to an electron, abbreviated +10e. A proton decays to produce a neutron and a positron. It can capture an electron. The nucleus captures an electron from the surrounding cloud or orbitals. The captured electron combines with a proton to form a neutron. The neutron may subsequently be emitted. When radioisotopes decay, they can change into new elements. Consider equation 1, the decay of naturally occurring iodine-131 by beta decay. A neutron within the iodine nucleus decayed into a proton and an electron. This decay increased the atomic number by 1, thereby producing an isotope of the element xenon. This change from one element to another is called transmutation. So we can tell that we got a new element not just because instead of I it's Xe, but look, instead of 53 protons, we have 54 protons. And it spit out an electron. Similarly, equation 2 shows that uranium-238 decays by alpha emission. The atomic number reduces by 2, because there's 2 protons over here now. And the mass number goes down by 4, so it was 238, now it's 234, because of the total of 4 AMUs over here in the helium nucleus. And it produces thorium-234. Transmutation can occur through artificial means. Physicist Ernest Rutherford bombarded nitrogen-14 with alpha particles emitted from radon. Okay, so he took the nitrogen, he slammed a bunch of alpha particles into it, and look what he produced. He made oxygen plus 1,1 hydrogen. The result was the first realization of an alchemist's dream, changing one element into another, even though no precious metal was involved. Since Rutherford's time, nuclear scientists have artificially produced an entire series of elements, trans-uranium elements, or the elements with an atomic number greater than 92, and new radioisotopes by colliding atoms, particles, and ions together in devices called particle accelerators. Particle accelerator is a complex electromagnetic apparatus used to study the structure of the nucleus. So our trans meaning beyond uranium. So atomic number greater than 92 are elements that scientists have made artificially. If you see an element that has 3 letters in the abbreviation, That is one that scientists around the world are still confirming that other scientists got to exist. Once they all confirm and agree, then they give it a name. Particle accelerators work by moving particles at high speeds. So this is an aerial view of the Fermi lab, and this is the particle accelerator inside the Fermi lab. Scientists use particle accelerators to study the structure of atomic nuclei. A particle accelerator contains a source of electrically charged particles. The particles may be electrons, alpha particles, or ions. The particles travel in a vacuum. As they pass through a series of electromagnets, they are accelerated to near the speed of light, 186,000 miles per second, or 2 times 10 to the 8th meters per second. Even small particles like electrons have great energies at this velocity. The high speeds are necessary for charged particles to make it past the electron clouds to the nucleus. The energized particles smash into target atoms. Upon collision, the target atoms may form new elements, which is transmutation, and release other particles and radiation. In some accelerators, the protons and neutrons of the target atoms break down into quarks and other subatomic particles. Some particle accelerators have circular paths. The first accelerator was made by Ernest Lawrence in 1929 and was called a cyclotron. The cyclotron had 2 D-shaped electromagnets. Electrons were injected into the cyclotron, and the alternately charged Ds created an oscillating electric field that accelerated the electrons. The electrons traveled outward in a circular path as they accelerated. At the end, they hit a small metal foil target. A detector sensed the types of radiation and particles. Compared to today's cyclotrons, Lawrence's was rather weak and could not reach velocities near the speed of light. However, today's accelerators use rings of electromagnets that are kilometers, so miles, in diameter, to generate the necessary speeds. The cyclotron at the Fermi National Accelerator Laboratory in Illinois is 10 square miles. CERN. CERN is the European Organization for Nuclear Research. CERN's New Large Hadron Collider is 17 miles in circumference, and particles in it attain speeds of 99.99% of the speed of light. The United States contributed $531 million to help build the particle accelerator and design and build key components. Approximately 1,600 U.S. scientists, engineers, and graduate students are involved in the research effort. And there is the cyclotron timeline if you enjoy looking at that with what's going on. Some particle accelerators are straight. Not all particle accelerators are circular. Some, including the Stanford Linear Accelerator Center, or SLAC, are straight-line accelerators. SLAC uses a long 3-kilometer or about 2 miles vacuum tunnel to accelerate particles. The rapid particles then travel around a storage ring where they hit different types of targets depending on the experiment. The electromagnets of SLAC use copper tubing and waveguides to accelerate the electrons. Detectors at the end look for radiation, particles, particle velocities, particle tracks, and even subatomic particles. Subatomic particles like quarks and leptons leave trails in bubble chambers after collisions. In particle accelerator collisions, transmutations with short half-lives are often formed and decay further into other particles. And these are the trails left. See, it's kind of pretty. Accelerators in medicine. Particle accelerators are used in medicine to deliver radiation to cancerous tumors. Electrons are accelerated and focused onto thin metal foil targets. When the electrons hit the metal atoms in the target, the collision produces X-rays. Nuclear equations can represent transmutation. Nuclear equations represent the changes in mass and atomic number that occur during nuclear reactions. Consider this reaction. You have uranium-238 turns into thorium plus a helium nucleus. The atomic number is on the lower left of the element symbol. The atomic mass is in the upper left, and the charge, if any, is in the upper right. For a nuclear equation, the total of atomic numbers on the left of the arrow must equal the total of atomic numbers on the right. So, 92, 90 plus 2. Similarly, the total atomic masses on the left must equal the total on the right. So 238 equals 234 plus 4. Mass and energy are conserved in nuclear reactions as they are in chemical reactions. Energy is given off in the form of electromagnetic radiation and or heat. What is X in this equation? Okay, so we have 239.94 Pu plus 210 N equals X plus 0, negative 1 E. All right, so all the top numbers need to equal. All the bottom numbers need to equal. Go ahead and pause, see if you can figure it out. So the total atomic number on the left is 94 plus 2 times 0, which is 0. And that has to equal X's minus 1. So 95 equals X. So the atomic number of X is 95, which is equal to Americum, or AM. The total masses on the left side must equal those on the right. So 239 plus, there's 2 of these, so 2 times 1 equals X plus 0. So 241 equals X. Therefore, your official answer is 241.95 Americum. Radioactivity can produce new elements. Unstable nuclei decay to stable ones by giving off radiation, particles, energy, and or heat. You can have alpha emission, a helium nucleus, beta emission, a high-speed electron, gamma emission, electromagnetic waves. You can have positrons. You can have an electron capture. The nucleus captures an electron from the cloud. The electron combines with a proton to make a neutron. The neutron may be emitted. Radioactive emissions can change the composition of the nucleus and produce new elements and isotopes, which is transmutation. Particle accelerometers smash high-speed particles into target atoms to make new elements, radioisotopes, and radiation. Transmutation of elements occurs through the decay of natural radioactive elements. Transmutation also occurs through collisions of atoms at high speeds. All right, let's take some notes. I did this one a little different. Figured we'd read first, then we'll go back and we'll look at some notes. All right, for our notes, I just left the beginning paragraph from the student guide and our goals and keywords and pronunciations. Particle accelerator, a complex electromagnetic apparatus used to study the structure of the nucleus. Can be linear or circular, but miles in size. Use electromagnets to accelerate particles near the speed of light. The speed of light is pretty much the fastest that scientists believe that anything can go. So that's why they use that. Detectors at the end look for radiation, particles, particle velocities, particle tracks, and subatomic particles like quarks or leptons. Transmutations with short half-lives are often formed and decay into further particles. Transmutation in nuclear chemistry, the change from one element to another. And so I gave an example, I made it up. 100 300 ZZ plus 1 electron yields X plus 3 neutrons. What is X? So hit the pause button. And remember the top numbers on this side, so 100 plus 0, have to equal the top numbers on this side. X plus 3 times 1. So the top number is 97. Bottom number, I have 300 minus 1 equals X plus 0. So it is 299. And that's it for this one.